Hi, everyone. Okay, we are continuing our exploration of the basics of elliptic curves. Part one was elliptic curves over real numbers and an introduction to the group law for general elliptic curves. So now this part is elliptic curves over rational numbers, and in particular, proving that the sum of two rational points on an elliptic curve will uh, make a third rational point. And then the last part will be elliptic curves over complex numbers. Then we'll move on to modular forms.
When elliptic curves get really interesting, and where I think we're really going to be going with them with our study, is when they're over rational numbers. So that means that if the coefficients are it means that the coefficients are over the rational numbers, and we're looking at so if we have 2 points that are rational numbers, the interesting thing here is that the third point will also on this line on this curve also be rational. And this might look familiar to you. It's very interesting. This is the exact same process that we were doing in the last video, where we took unit circles, we took a line -1, 0, and another point x, y, and we proved that if the slope of this line is rational, then this point will be rational. And if that point is rational, then the slope of that line will be rational. So we're doing something very similar here. So the interesting thing is that when you do the addition operation on these elliptic curves, if you're starting in rational numbers, you're always going to stay in rational numbers. More abstractly, for any field, if you start in the field, you'll stay in the field. So that's very interesting. That's what we're going to prove now. With again some just basic algebra. It's very similar to what it was last time. So if we have, let's say that P equals xp yp, Q equals xq yq. Okay, these are all rational. All elements of the rationals, which means they're just fractions. Then the first thing is the slope. We need to find the slope again, same way that we did last time. Let's look at another. So if we have, say, these two numbers going up here to R, so this is Q, this is P. What's the slope? The slope is always the rise over the run. So we need the difference in y's over the difference in x. So we have here the difference in y is yq minus yp. The difference in x is xq minus xp. This is the slope of this line. So what we're trying to prove is that if P and Q are rational, then R is going to be rational as well. So let me switch notebooks. So now again, we do something very similar to what we did last time. So we have the slope of the line, as always, is y equals sx plus d. That's just the standard slope, standard equation for a line. We need to, if we take this equation and solve it for the y's, then we just multiply the bottom by both sides, and we get that yq minus yp equals s times xq minus xp. Okay? And then we also have the equation of our elliptic curve. So remember, what we're doing here is we're looking for, we have a system of equations because the line intersects the elliptic curve. So at these points, x and y are going to be equal. So we have the equation of the curve, we have the equation of the line. So that's a system of equations. So now we can find the values of those of the coordinates. So all we're going to do is take, same thing, this is again the same thing we did last time. We're going to take y and put it into the y squared. I'm going to switch pages because we're going to need some room here. So we have y equals sx plus d, y squared equals x cubed plus ax plus b. So we're going to plug y in to this. So we end up with sx plus d squared equals x cubed plus ax plus b. Now we're just going to move everything over to the other side and multiply it out. So we set it equal to 0. And then we're going to look at some roots if we can. So we have first, okay, let's do it. We can do it in one shot. So we're moving this over to the other side. Or maybe we should, which way would be better? Let's multiply it out first. So first we'll multiply this out. So we just do FOIL. So it's s squared x squared plus 2s dx plus d squared equals x cubed plus ax plus b. Okay? Now we can move everything over to the other. Now we'll move everything over to the other side. So 0 equals, so there's x cubed, and then minus s squared x squared. Are there any other? Nope. Then we have minus 2sd x plus ax plus b minus d squared, right? Boom, 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 boom. Okay. Now gather terms again. So we have 0 equals x cubed minus s squared x squared. Here we can gather the terms. So we have plus a minus 2sd x plus b minus d squared. Now, the next thing we're going to do is very interesting. This is some algebra that I don't think we do very often. But we're going to equate the coefficients. If two polynomials have the same coefficients, then they are the same polynomial. So what that means is it's a very obvious statement. But if you have 2x squared plus 3x plus 4 equals ax squared plus bx plus c, then a equals 2, b equals 3, c equals 4. Okay? So take a pause here. So there is a polynomial that has the following roots. Okay? There's this polynomial, or there's a polynomial that has xp, xq, and xr as its roots. So if we multiply this out, let's see what that equals. First, let's just leave this one and multiply these two. So x minus xp, and then x squared minus x. Oh, we're just gonna have to keep that separate. Minus xr minus xrx minus xpx or xqx, and then plus xq xr. Multiply it out one more time, and so we get x cubed, and then minus xrx squared minus xq x squared plus xq xrx, and then this minus xp x squared plus xp xrx plus xp xqx minus xp xqxr. Well, it'll be a miracle if we get this right, right? Now let's combine terms. So we have x cubed we have minus xr minus xp and minus xq. So we can do plus, and then each one of these, minus xp, minus xq, minus xr, x squared, then we have, okay, this is interesting, plus xp xq plus xpxr plus xqxr x, and then finally minus xp xq xr. So that looks right to me. So here's the thing. We have a polynomial, right? X cubed, x squared, x, and x to the 0. Here's another polynomial, x cubed, x squared. So we know that this polynomial has these roots. If we set this polynomial equal to this polynomial, then this polynomial will also have these roots. So in order to do that, we can just look at minus x squared and set minus s squared equal to this, or s squared equals all of those plus. So let's do that. So what we want is s squared equals xp plus xq plus xr. So we're looking for, what we're trying to prove is that r is rational, okay? That x, r, and y are rational. So if we just move everything over to the other side, we have xr equals xp plus xq minus s squared. We already know that s is rational. We know that these two are rational, so x, r, has to be rational. Now we have to find y, but we know that if we look at the graph again, we have P, Q, and R. We know that S is also, it's the same slope. So we can say that that YR minus YP equals S XR minus XP, right? This is the same thing we did before. We have the rise between R and P over the run between X and P, and then we multiplied it out. So it was YR minus YP over XR minus XP, and then we just multiplied it out, so we got that. Move this over to the other side, and we have YR equals SXR minus XP plus YP. Again, this is rational. We just found out that this is rational, and that's rational. So YR is also rational. So we've shown that P plus Q, that when P plus Q, it's closed under addition, so that R is also an element of Q. Okay, so the last thing we have to show is, so we already showed that if P and Q are opposite, then it's just a vertical line up to infinity. That's just by definition. And even over here, even if Y and Y are the same, if P equals Q, then P plus Q equals 0. Again, it's just a vertical line up to infinity. But we still have to account for the case where P equals Q and it's tangent to this line and R is up here. So in this case, we know that basically it's basically P plus P. In other words, 2P. So what we want to do then is, what we have from before is that we showed before that XR is XP plus XQ minus S squared, and YR then is just the slope plus YP. Okay, so we're basically just using those again. So P plus P is minus 2P because it's the opposite point, right? You go down. So we have that XR then equals S squared minus XP minus XQ equals S squared minus 2 XP. That's X. So XR is just S squared minus 2 XP, almost the same thing. And then Y squared again, or I'm sorry, YR equals YP plus S XR minus XP. So again, it's the same slope, using the same slope line, but here it's XR instead of XQ, and we just move that over. And then again, because it's minus here, then we're using the minus of the YP. Oh no, I'm sorry, no, that's not right. It's because it was minus over here, so it's plus over there. Okay, so these are the two for X and Y. So we've shown that these two are rational, but I still have to show you what the slope is. So the slope, unfortunately, this is the first point where we almost got out of this video without having to do anything more complicated than algebra once again. But in order to find the slope of this line, we're going to have to use calculus, because we're going to have to take the derivative of the line right here. And it's a little bit ugly because it might be unfamiliar because it has two variables. So it's x cubed plus ax plus b at that point. So we're taking partial derivatives here, and if this is something you don't know, basically the way you take a partial derivative is if you're taking the derivative of this with respect to y, you just count everything else as a constant. And then when you're taking it with respect to x, you take everything else as a constant. So what we're going to do is move the y over here, or actually move the x's over. I guess it doesn't really matter. But yeah, let's move the y over. So we're just going to define a function. Okay, so now we're just going to take the derivative of f with respect to y, the partial derivative of f with respect to y is minus 2y, and then these are all constants, so the derivative of them is nothing. So that's the derivative with respect to y. Then we take the derivative with respect to x, and now this one's constant, it goes away, and we get 3x squared plus a, and then that one goes away too. So what we need is, this is the change in y, this is the change in x. So we need to find the change in y in terms of the other things. So we have that dy, here, do it this way. So move this over to the other side. So we have that df equals minus 2y dy, okay? And then divide this through, so we have dy equals, divide this through df over minus 2y. That's the partial derivative with respect to y. Do the same thing here, just move this up, move that down, and we end up with dx equals df over 3x squared plus a. Now, let me switch one more page. Okay, so what's the slope? We want the slope of this line. The slope is the change in y over the change in x. We just found out that the change in y is df over 2y. And we had a minus sign. I'm not sure about that. And then dx equals df over 3x squared plus a. Okay? Just plug these in, and we get that s equals df over 2y over df over 3x squared plus a. Flip this and multiply, equals df over 2y times 3x squared plus a over df. Those cancel, and we end up with 3x squared plus a over 2y. That, once again, is going to be rational.
Okay, that is the end of part 2, elliptic curves over rational numbers and the group law with rational numbers. So part 3 is elliptical curves over complex numbers, and then we will move on to modular forms. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.